there. And two of these 8 nodes are equipped with NVIDIA GPUs really for doing high performance computing. For performance in an operational environment, when we're currently using 4 storage nodes, so 4 times 192 terabyte, we get a read-write performance currently between 1 gigabyte per second and 5 gigabyte per second. So much less than we expected. We have to work a little bit smarter and harder there. And when you use it as a block storage, it's a little bit faster. But it also depends. This means the redundancy factor. When you have a higher redundancy, it takes longer to read and store the data. Good. When we're speaking about big data, what do we need to do there? For example, we made a reprocessing of the full global memories. This was an ESA mission for 12 years. Altogether, we have 13.3 and a lot of zeros measurements, and this should be computed. In the beginning, with the algorithm we selected, it would have taken, I don't know, more than 1,000 years on a quite good computer. They were always using trays. They found those trays in Finland. They were used just for military reasons, but Finland didn't need them anymore. So ESA got those trays. And it was too expensive to operate it there. We got this algorithm. The algorithm is called GRASP, General Retrieval for Aerosols. Aerosols are floating particles in the air, and we want to find out which particles are these. There are more than 800 different particles floating in the air, and from satellite, this algorithm can find out which particles these are, the size distribution, and so on. It was a very complex algorithm, and still is, with 50,000 lines of code. And it was very computational intensive. It was highly memory bound, and it was already optimized several times for speed. It was developed by NASA for over 10 years, and then for the next 10 years by ESA and NASA together. And then we came to ESA, told them that we can speed up this algorithm by a factor of 100. So this meeting with ESA took us 30 seconds. Then they said, this was in Vienna, then they said, okay, visit us in Italy, at Esslingen, where we all have the data. And the first sentence what they said is, we don't believe you a word. So they handed us over the algorithm, handed us over also some test data sets, which were defined by 1,000 times 1,200 kilometers, which is about the size of 4 times Germany, and a data set of 2 months. And when we calculated it, it took us quite a long time, and we did all those accelerations based on GPUs, so the graphic cards. And we really compared it, or not we compared it, but ESA compared it with a 6-core i7 3.8 gigahertz machine, and then the NVIDIA Titan GPU. And we got all together to the original code effect of 117. So that's good when you can reach it. It's not always the time. We also had always the case. We also had luck there. But when you reach it, then you also have to adapt your development process. So while the developers check in code to the source code repository, of course, then you make all your structural standards and code quality tests. You make your unit functional reports test, maybe also numerical stability, so that it runs and reproduce a reproducible result on other machines too. But then once a day, we deploy the complete code to a cluster and let it run there on a larger data set. And then we also get a report on scalability, on interoperability, and there's a continuous cost projection. So when ESA says, okay, I give you those 13.3 trillion data, please do a complete reprocessing, and we have to do this every 2 years, then we have to tell them how much it costs. costs them, I don't know, 3, 4, 5, 600,000 euros. And of course then you must make sure when you press the start button of the application and it starts to reprocess for the next 1 or 2 months, that you really can do it with this money. So we have every day we have a cost projection, because just one line in the source code maybe let the code take 10% longer, and then you have, when you're thinking about 300,000 euros, then you have a cost increase of about 30,000 euros. Good. What we also did is that we modularized Dress quite good, and therefore it was able then to, was able to implement the algorithm in a way that it also reads data from several satellites. We currently are able to read data from more than 40 satellites, and because it's a complete physical model, it can not only calculate atmospheric parameter, it can also calculate surface parameters, so the backscattering of the Earth. When the sunlight gets to the Earth's surface, it's backscattered. And the pictures are quite good, but when your scientists or the developers, when they see some data which they don't believe, let's make this one, could there be such a cloud over here, a dust cloud over here, or this one, then you have to give them also data from different satellites. So you have a visual composite of the same. A composite is that you collect all the data of, for example, 1 day or 1 week or 1 month, and then show it to them so that they can do a comparison and that they see, yes, this algorithm is really working quite well. So you have to work quite good on a validation framework that people really can validate your data, what you're producing. Otherwise, you are calculating for 300,000 euros just for fun. And of course, what you also have to do is that you have to make your data public, so that the other institutes also can validate your data too. And this is what we made. And here, ECMWF is the European Center of Medium Weather Forecast. They have a quite good assimilated model, and this is currently the operational service of ESA, and that's the operational service of NASA. That's our algorithm, and this is from this institute what they think is best, just from comparing it visually, our algorithm fits best here. Okay, time is over, I've seen. Very, very fast, 20 minutes. I only have one interesting thing. So when you build services in big data, many companies have to work together to make such a thing happen. And the problem is then, how do you make revenue sharing? And the keyword or the buzzword currently is their smart contracts. So we currently, when a user accesses the data or accesses the service and does something with the service, then we really log everything what he is doing and where he is accessing the data, this set of data, and how much memory he needs and how much CPU he needs and everything. And then we have a cost function where we calculate the cost. And of course then that's the smart contract. This cost is then, or the revenue is then given to all the companies acting. And the next step is what we are developing here, to do this also with a blockchain technology so that it's safe to use it. Okay. Give me 2 more minutes. Now it was very fast. So, okay. Yeah. Good.
This one. Okay. So if you have any questions.
Was it too fast?
Sorry, I missed the first minutes. So this, I guess, is a showcase of your product and how you analyze it with all the data. there are a lot of numbers and everything else. I want maybe there is a possible to summarize or give us a conclusion of all of this presentation.
Yeah, it's very so to mesh all the data what you get from satellites, also with data from Earth. It's quite complicated. You have to have a good data center. You cannot do this, for example, on Amazon or whatever. You have very good algorithms, scalability and performance. You have to keep in your place also in your development process so that your developers really perform on an everyday basis.
So because you mentioned that performance was critical to your application, what language or frameworks did you use? And what were the competitors that lost out?
Okay. For R&D we are using Python, and then for the real implementation we are using C++. And competitors are, for example, as you know it in Europe, it's Airbus, DLR, this old aviation, and all those companies. Most of them are using still Fortran. But with C++, you have a quite good framework that you can write your algorithms for the CPU, and then also with some very small extensions also for the GPU.
Just a curiosity, you said your data center is on-premise.
Yeah.
Is there a reason for that?
Yes. When you store about, let's say, 1 petabyte of data, you go to Amazon and ask them if you can store the 1 petabyte. It costs you in a time frame of about 3-4 years, it costs about 5 times more than when you build it up on your own.
And just a follow-up question, do you have an archiving policy or retention policy on the data? Or do you just keep this forever?
Mm-hmm. There are a lot of policies, so when are you allowed to store data with a replication factor 1, 2, 3? Then also when are you allowed, there are some products which we store, which are used very seldom, which we store them on a tape. And also how you delete data, because when users are playing around in the beginning, they produce a lot of data, and they have some, let's say, directories where they can play with the data, and this is then deleted every 24 hours or for 1 week or whatever.
Thank you.
Okay, any other questions? Cool then. Thank you.